So let us understand where we are in this course. You had seen a number of lectures, basic architectures, a lot of detail that you had seen in the past. So I would like to build on top of these and move forward. So how do I do? So let me start with setting the background that is required for this purpose. So what we want to look at is what happened when the deep learning really hit on the ground and kept all of us busy from post 2012, 13, etc. So this significant piece of work which showed that image classification at scale can be done accurately. So what it had shown to us, what's the message that we got out of it? Can any one of you tell me what is the primary message that we got with the success of AlexNet and similar networks for a classification problems that we had seen? What's a single message that we got? Who cares about how well we do on ImageNet? Nobody cares. It's a specific task, isn't it? So there's a specific task or on some data set, somebody has put up some test data and you're running your code and getting some number. That is one part of the story. But that is, of course, that's a metric or that's a way of appreciating that something happened. But who cares? What is a message for you? Anybody wants to answer? You can type in your chat. What is a message that you got when you found that this happened? This and similar. I just put a class of things around it, saying that look, all the such networks, AlexNet to ABCNet to every CDE net, all such things, all such network, everybody's network succeeded. What did happen? No answer. It's a silent class. That's bad. Allowed to call you by name and ask answers. What is the message that we got from this level of things, the success of quote unquote deep learning in that era? No? Yes, there is an answer coming. Going deep will get more clear information on anything. Yes, Srinivas saying that going deep will get more information on anything. Yes, nice. Some more answers. That is, going deep is important. Yes, depth matters. What Srinivas says is depth matters. Fine. What else? Layers of learning. Okay. What more? Okay, there's a much simpler message for us from that. That is, supervised learning works. If you have sufficient examples of input output, you have sufficient compute power, memory, the layers or depth or parameters or whatever, you can design a reasonably good architecture. You get very good results. Seems simple, isn't it? So isn't it enough for us today to live? If that is true, that if you have sufficient examples, sufficient compute, I'm using the word, every problem, quote unquote, every problem in the world can be solved today. Isn't it enough? Are we missing something? That's not enough, because this way of brute force way of solving with data on everything is not going to work. So this created a lot of things after that, people worried about it. So this data-driven problem solving, So I'm abstracting this. Remember, today, if you want to do research in this space, you need to have the capability to abstract. You need to have the capability to abstract the architectures, how things work. So if you look at the picture here, what is that I had shown here? So you have a picture and you want to have a classification saying whether this person is walking, jumping, running. I don't know if you ever worked on such problems in images or videos. You will remember, yes, this is a well-known problem. Or if you want to say, yes, this person is like a male, female. So you can decide a number of classification problems on top of it. How does such architectures work? You have a number of layers where you offered some convolutional layers. Then at the end of it, you have some fully connected layers or a classification style layers, and that provides some labels. And we are able to say whether this person is walking, or this person is jumping, or this person is running, etc. So this is what we solved. If you look at the previous picture, this is what we solved. It was not action, it was objects, possibly objects or scenes or whatever it is. So it classified that this is a steel drum, this is this object, this is an elephant, this is a tiger. That's the style of things that we did. Now this exactly the same thing can be applied, and it works here. But something more important happened, that we suddenly realized that all this big left block that you see is reusable. If you formulate this problem as, say, regression, maybe with a different loss function, I can predict, say, a number, say age is 40, or the location is like a XY or in some coordinate. Looks that, so what is the message here? So the early layers here were doing exactly the same, and they were providing the rich information. And the later layer, just when the problem changes, we need to change the some layers and the loss functions or goals, etc. You can also predict not just a number, not just a label. You can also predict, say, things like graph and tree on top of it. What are the joints of the body, how they are connected, etc. Cool. And you can also do train a network all together in one go also. So if you are short of data, you have data from different tasks, use all of them together. So there are many interesting innovations happened today to do that. So what you understand here now, if you look at that, that orange piece that I have, I don't know what color you see there, that piece has the understanding, the meaning, the essence of the input. Once I have the essence of that input, I can use it to present for, or I can use it for solving different tasks on the right hand side. Beautiful. So what is important is to get that essence. By removing a lot of potentially irrelevant things and get that essence right. If the left block can do a great job, and then the right blocks can do the appropriate specific problems of interest in that space. This is what happened very soon after the breakthrough of deep learning. Clear? Any questions? I don't want you to just relax and sit relaxed and do that. Do something, a question, answer question, write questions, answer questions in the chat. Have some energy. It's a morning session. You can't be tired. Okay. So is it clear? This entire thing you are able to see where it connects to your work or what you have been studying? Yes, good. Balaji, good. So this is exactly the story. So this happened. Now the next question comes. There is a next piece happened parallelly. This set of people started from the other end of the story, that I have the meaning, or I have a distribution, I have a set of representations. From there, what can I do? Can I generate realistic data? A number of architectures, a number of approaches, a number of things came over years. I think Andre Karpathy's work, I think 2015 or 16 time frame, possibly. Remember, not so long, not very old. So he was able to generate, like a technical paper, some theorems and proofs. He was able to generate things like William Shakespeare. So he was able to generate, say, music like, say, Beethoven or whatever it is. So the capability to synthesize started to surface with the set of architectures. So these pictures are not photographs of real humans. These are not paintings done by great artists. These are generated by neural networks, starting from some understandings or symbols or representations or embeddings or whatever you call on the left-hand side, using a thick blue block of some neural networks. It is able to generate voice, just like you or I speak. So this is what happened over time. Another set of stories. So you see the two complementary pieces now. Now, what is natural then to happen? It's quite obvious now for you what I'm going to do next. You can put them together. When you put them together, you have architectures which can do encoding and decoding. Now, you may call encoding as where you find that extract that essence. Decoding is from the essence you decode into something that the end user or the humans understand or perceive. So you have now a seamless way of transferring the essence from one modality to another modality. I'm done. My primary job is done today. Okay. Any questions? I told you I'll finish before time. Yeah, tell me. Any questions? Is this architecture clear to you? Oh, this is a very silent class. Yes, Srinivas is coming back. Difference between multimodal and cross-modal. Yeah, I shall say multi-cross. Cross is like when you go one from other. Multi is usually used when you are using all of them together. Yeah, nothing. Different modality. Modality also generally people understand it as speech, text, vision, etc. But you can also have many other modalities in the story. Yeah. Good. Remember, there are silent people. If you look at after the lecture, what is always the case is I'll ask questions. So get ready. So if you want to avoid quiz, you should ask me questions. Okay, so this is the story. So this is what completely now working today. Now, what is important is so this gives us a very beautiful set of opportunities to do interesting things. I remember this architecture also allows me to go from text to text. I can move from an English sentence to a Hindi sentence, and I call this as a machine translation. Okay, now quiz starts. Okay, so I have an architecture now like this, which is used for, I give a black and white picture as an input. My output is a color picture. This works. Okay, don't worry, this works. Now my question is, why does it work? That's the first question. Intuitively, how do you answer this? Why does it work? Question one. Question two is, how do we get training data for such tasks? So it's very difficult sometimes, like you need to get training data for all such tasks. How do you get training data for such tasks? There are two questions. What are the answers? You can answer for question one or question two. At least one of them you can answer. Or both. Or you can say this will not work. What is that? Why are there are around 30 people here? Why are they all of them silent? Allowed to call you by name? Yes, reinforcement learning. My God, no reinforcement learning, Uma. I told you this is all these methods work with simple back propagation. Like you have a loss, you do that, you train that, isn't it? So you provide input, you provide output, you train. You define loss, you do train. Nothing, no fancy thing beyond. Any other answer? Why does it work? How do you get training data for such tasks? Why is this class is very silent? All of them are not allowed to. I can unmute them. I'm a co-host. I can unmute them and ask questions, isn't it? Where are people here? Why people are silent? Why does it work? It works because the essence that you have learned. So the first part is easy to answer. Like, why does it work? It works because your encoder earned the essence of it, and the decoder is able to generate from the essence. So the yellow piece in the middle or orange piece in the middle is what it's telling. It is a butterfly in the garden. Now, it is butterfly in the garden is what is that orange piece. And here are the pixels of butterfly. Here are the pixels of like a flower. All this understanding that you may have from that is all captured in that number of bits that you have in the middle. How do we get training data for such a task? I won't allow you to move forward without answering that. Okay, Srinivas is saying, how the model is determining the wings of the butterfly is only orange instead of other colors. Very good. Maybe it is due to more images that got trained. You are right, Srinivas. You are perfectly right. You are right. Good. You are right. So this is why it says. It has seen a lot of butterflies of this color. It had never seen butterflies which have some, I don't know, some green color butterflies. It has not seen. It has not seen leaves which are red and pink. It has seen only green leaves. That is why it is painting leaves as green. You are right, Srinivas. Devika, many similar colored images can be given as training data. Yes. So just take that. Oh, you're answering the second question. Many colored images. No, what? So you want to give input and output, isn't it? How did we train AlexNet? I gave a picture and told it is a tiger. I gave another picture and told it is an elephant. I gave another picture and told it's an auto rickshaw. So I have an input, I have an output. This is how I trained. So I can also do the same. So I need to recruit now a lot of artists. I give a black and white picture, ask artists to paint it, and then give for training. Is that true, Devika? Can I do that way? I take black and white picture, I get some nice artist who will paint it and give it for training. Can I do that? Should two artists paint the same way? Or how do you create training data for this purpose? X and Y. X is the input, Y is the output. Machine is made to learn that leaf is green color. Yeah, you're right. But how do I give training data? I want to give input, I want to give output. My input is an image, black and white image, output is a color image. So how do I create? I take a black and white picture, ask artist to paint and give it as an output. No, why this is a very, very slow response. They're all like watching it on a phone and lying down on the bed. Where are the answers? No smart guy in the class who will answer this question? This is a very, very nice answer, very simple answer. Can give other images with leaves, sir. Like, yeah, but Balaji is saying, if the same set of both gray and color input of the same image will help prediction. Yes, we should give the same, isn't it? So I should give the input as a black and white image, output as a color image, then only it will train. Balaji, you're right. But how do I create it? I need so many artists to train such a deep neural network. Of course, there are artists may be ready to sit and paint. I don't know whether they will enjoy painting such pictures. If you're not answering, I feel bad. Like, this is a very, very nice, clean, good answer that you should all learn how to do that. That makes you a researcher. If you're not able to answer it yourself, you are struggling with how will you do research yourself. Tell me what is the answer. The answer is very simple. You never take a black and white picture, paint it, and give it as an output. You do actually the opposite. I take a color picture, remove color, and give it as an input. And there is no shortage of color picture on internet. So there is no artist required, there is no human required for creating the training data for this network. Agreed? That is a beauty. You have to understand the smartness in research. The smartness is in not going from left to right, take a black and white picture, hire hundreds of artists, ask them to paint and create the training data for it. The smartness is in like a freely available data, use it, remove the color and give it as an input and create the training data. And that is what is today required if you want to solve a new research problem. That's why I spend a little bit extra time on this question, is because you should appreciate how such smart formulations are changing the way you are doing. If you just look at textbookish person and understand how to do, you're never able to think that way. You should be able to think, try your solutions, try your ideas, innovate. So this is the key for success today. Okay, so now to summarize, so supervised learning has demonstrated a success. Deep learning architectures, learning with backpropagation, we are quite comfortable. Learning to recognize and learning to synthesize, both we talked about, and strategy that works across modalities. So the strategy is in general true for both. So this is where I am right now. Okay, so now let me move forward. So we saw this model now, which can translate from one modality to another modality. It could be from, say, image to speech. And we also saw this example of black and white image to color image. Now let us go further and ask, we take a few examples here and see whether this is working well. So you possibly we don't have to worry about all exact details. I just take a classical example of an OCR. And what's an OCR? OCR is all about there are text printed or written in the image. Okay, it could be printed, it could be handwritten, it could be painted, it could be on this flat surface, it could be on curved surface, it could be horizontal, it could be vertical, it could be at very places you have. What is important is you want to convert that into a text form, a set of, say, Unicode or ASCII or whatever it is. So you have you have to translate from an image piece to a text piece. Very, very simple, like a modality transfer here. Now, how do we do that? So the same story again. So we want this really, and if you ever want to look at this now, so let me come back and motivate you why such data-driven models will be of immense use today. See, if you ever want to build a solution for, say, Indian languages, look at the situation we have. So the number of scripts or languages that we have. Now, for every modality now, if you want, like a printed, typed, handwritten, online, seen text, there are so many variations. If you ask anybody who works in OCR, they say all these are different domains. So if you want like every state in the India to have groups which have expertise in all these, it is impossible. And now this is what happened in the past. We formulated this problem with a lot of knowledge from the script, by segmenting, by character recognizing, by joining them, by working on matras, this, that, like all languages had interesting papers came out. So the number of things required is becoming extremely large. But today's data-driven models give us an advantage that maybe the same strategy helps us to take all these to some level with ease. Of course, there is a domain knowledge of the language, script, all of them will come to be useful after once you reach there. Now, so how this was formulated? So to motivate you, very similar to the, say, for example, the machine translation formulation. So here, input is a sequence of image strips. Output is a sequence of, say, text string like Unicode sequence. And then you can do a translation from one sequence to another sequence. If you have one sequence as a Hindi sentence, another sequence as a Telugu sentence, you say it's a translation from one language to another language. Here it is translating in image strip sequences. So think of this image, take a set of strips and say, yes, here is a set of strips, and my output is a set of Unicode, sequence of Unicodes. What I need to do is exactly the same architecture. Now, any architecture that we use now today for such translating across two sequences is applicable here. Now, when you do that, it is one, we are able to translate, but or we are able to recognize the text. There are a few important things that you can do. You can actually do now, as if you look at on the left-hand side, traditionally what we have been doing is we are doing a lot of image processing. If anybody who has worked on image processing will understand, given the type of image that we have, like with sometimes cuts, with sometimes blobs, breaks, so to get all these separate characters or isolated glyphs, pieces, and then recognize them accurately and arranging them, so that there's a lot of dirty image processing required. And they fail very frequently because of the robustness issues in the algorithms. This is taken care by this sort of model. This is the beauty of it. In addition to the lot of other things that I talked about, how do you rapidly prototype, how do you scale across languages, scripts, etc. I'll take another example of this. So if you look at the example of text to speech, what is the input here? Input is a text, output is a speech. Now, how do you train such models? So you have now somebody reading out. So I show a sentence, you read out that sentence. I have input is text, output is speech, and you are training a network such that I can translate from text to speech. So I'll show you an example from one of the TTS that we trained. This data was collected in locally. It was not very complex. One of our group members spoke for a few hours, and that we used for training this model. And here is it.
मैं लोगों के दिलों की रानी बनना चाहूंगी, लेकिन मैं खुद को इस देश की रानी के रूप में नहीं देखती.
I hope you can hear sound. Can you please confirm? Yes. Okay. Thank you. Thank you. Yeah. So the advanced.
हम सभी में किसी न किसी तरह की प्रेरणा होती है.
Remember, these are not recordings from the person. These are a person speaks a number of sentences. Now we use the same strategy. Now given a new sentence, speech is generated. So you see how it works. I'll go to still more complex space where this like a sort of like a relationship could be far more complex, because there is another piece, like it is not just the text, it is not just the images, it is not just the speech. There is a, so this tree could have a lot of interesting variations across these. By one should be able to predict the other. Today people talk about capability to do that. Can, given the say lips, can I talk about the speech? Or can I, from the speech, can I talk about the lip movements? From the lips, can I talk about the text? From the text, can I talk about the lip movements? So look how, or what, or all pairs of such transitions are also being appreciated for in this space now. So here's an example video which will motivate you that this is today successful. So given a video, you should be able to just read what goes on in the video by watching the lip movements itself. And a lot of people do that.
The government will pay for both sides.
We have to look at whether it works for the UK or not. It said security had been stepped up in Britain.
I hope you see now the utility of such a technology too. So it's an important issue to understand and read for people do that, humans do that. Not just because I cannot hear, I think I'll also argue that this is important if you ever want to perceive or understand what the other person is speaking. So for example, like when many of us communicate, the communication becomes far more effective if I can see the other person's face and the lip movements. And when the lip movements are not completely aligned, you feel that there is something going on. So here's an example. Now, can you do the reverse? Say, for example, given this lip movements from there, okay, or can you generate, say, for example, the speech?
Are present at 1 atmosphere of pressure. If there's a concentration, it's 1 molar. Liquids and solids are present in their pure state. So with that in mind, which of these is a plot of standard state?
The speech you just heard is completely generated by reading the lip movements of the speaker. We tackle the task of lip-to-speech synthesis in unconstrained settings for the first time. In this video, we showcase our results of our sequence-to-sequence approach for this task.
Now, if you'll pardon me, I won't keep him waiting.
We now show our superior performance in unconstrained real-world settings with 100x larger vocabulary and significant head motion.
Example, using loops and the regular style of coding that we do. You need to exploit certain instructions that the hardware gives you in order to speed up this process, and that's what you will see in any library that is provided to you. So if you actually disassemble that code and look at the example, using loops and the regular style of coding that we do, you need to exploit certain instructions that the hardware gives you in order to speed up this process, and that's what you will see in any library that is provided to you. So if you actually disassemble that code and look at the
B transpose P is equal to 1. What is the solution for this? Smallest eigen value of sigma, right? And you can P transpose P is equal to 1. What is the solution for this? Smallest eigen value of sigma. right? And you can
In addition to unconstrained single-speaker lip-to-speech results, we also show our results on multi-speaker word-level lip-to-speech.
Are being accused of
You have to understand that.
inflict prison and life in prison in the United as a result of
We end this demonstration with an interesting application of this task. In the event of speech corruption or loss, our model can seamlessly generate and fill in the missing segment to ensure a smooth user experience. The generated segment is fully inferred from the lip motion in the video.
Product of two linear concentrations where you have the order is 1 plus 1, the sum of the powers. So here's some examples. The NOBr breaking down into NO and bromine and hydrogen and iodine.
Okay, so I hope you got a feel of what is possible now today. Like you can transfer across widely different modalities very easily. Any questions at this stage? I always say, if you don't ask me questions, I'll ask you questions. No? No questions? Good. So you understood that you are able to move across widely different modalities and expectations today because these architectures are really, really powerful and complex and capable of doing it. They may be deep, they may have many layers, and a lot of things that you have seen in the last few lectures in this course that you have studied. So what is the story here now? So in the past, we saw two things from a machine learning viewpoint. One, Alex, that we started by saying the success saga of supervised learning. Then later on, we talked about the smartness required today when you do research in creating the training data without a lot of effort. Now that story threads takes to the next level. We are talking about how do you get a lot of free supervision. So the free supervision is available because you have videos which are created for multiple tasks in the past. And there is a synchronization between the lip movements, the speech, and so you don't create extra label data for this purpose. What you need is only like a curate the right amount of training data, the right style of training data from such repositories that are online. This is very, very important to appreciate today. How that smartness in the creating huge training data or whatever the specialized training data with free supervision is harvested or curated or created. So I just want to take one specific example for you to tell what is it. So if you want to look at, say, for example, if you want to know, think of you are interested in creating a classifier, which given a video at any point of time will tell you whether a lips and speech are synchronized or not. Okay. So what do we do? So you have a video, you have a visual stream, you have a speech stream, and your task is at any point you want like a classifier to say, yes, this is synchronized. No, there is a problem with the synchronization. That's a simple binary classifier, but with super high accuracy we need. So how do we create training data for that purpose? The smartness in here is, you can see the picture on the right-hand side. We want to create a lot of positive pairs by taking the right set of window or the exactly corresponding window from the visual and the speech stream, and creating negative pair by taking visual stream from somewhere and speech window from somewhere else. So if I give you a video now, you can create like lots and lots of such positive pair and negative pair without a human sitting and annotating. Once you have that, there are nice machine learning strategies of creating classifiers, which will say when it is positive, when it is negative. You can also use this contrastive loss. I believe you have seen somewhere in the past, such like a Siamese network, contrastive loss, triplet loss style of terminologies in the code somewhere. So they can be useful for creating such very fine variation so that you can get actually when it is exactly in sync or slightly out of sync itself. So you see that the beauty of how to create such a classifier from the video without being super like a human sitting and annotating or tagging it. Smart use of formulations. So when you solve problem, please look for such smart formulations. This allows you to solve problem which nobody else has ever thought in the past. Okay. How am I doing on time? I think my most jobs are done, so I think I should be fine with time. Okay, so now not just this, now you can also do the same. Say from the speech, or I can also create the lip movements. How do we do that? So you have an encoder, you have a decoder. Now you also saw this block of say sync discriminator if you want to appreciate that way. When something is in sync or not sync, we have a classifier that can be trained, and that can tell us whether our generated like a video is natural or not. So you build a capability to generate the right things by having a right discriminator. And remember the discriminator, we got it free in the previous slide. So how such discriminators can be obtained. So you have a face encoder. So now you also see the challenges because you're encoding stale. You may have your multiple encoders because the architecture that is popular for encoding an image may be different from the architecture that possibly is popular in the speech community. So you basically you use such blocks because every community has over years have refined and built such blocks, which now today we can reuse it. Just like say you never start coding say CNN from scratch. You never start designing an architecture from scratch. You learn a lot from what has happened in the past and start with the success, understand the limitations and failures, and take it forward in the next level. So here's an example.
All my troubles seem so far away. Now it looks as though they're here to stay. Oh, I believe.
Our LipGAN model takes.
So now this is the way we can generate such like a lip say videos. Now what we had seen till now is we had seen transnational models have a lot of interesting applications within modality, like across modality, OCR, TTS, machine translation, cross model, a number of things. A wide spectrum of interesting opportunities now. So for example, the example that I took was possibly in the space of say text, speech, and lips. Similarly, one could think of say sign language, gestures, expressions. A number of such modalities can you transfer across one to other. So as I mentioned sometime back, the modality is not just limited to like a speech or video or images or text, etc. So you can have many interesting modalities to work with. So another important aspect we saw till now is self-supervision. How do you supervise? How do you create such supervisory information from the data? How do you exploit the supervisory signals without a human sitting and labeling a lot? And very interesting such like a harvesting such supervisory free supervision available in the data in the form of self-supervision and many variations of that has been a very, very hot topic today. And many smart usages have resulted in big breakthroughs. So it's a very interesting space for you to appreciate and explore. And they also open up now a lot of interesting applications because you are able to do these things which we never were able to do in the past. So the applications of things like OCR, speech, MT, etc. are like a well understood. So I'll go a little bit more applications centered around say multi-model or cross-model style of things. Any questions at this stage?
Yeah, excuse me, sir.
Yes, please.
Sir, I have a doubt. When we are doing this, is it possible if the video, the person is moving or he's turning his head or something like that?
Yes.
If a person is, yeah, oh,
Yes. It's
okay.
possible. It's possible. Yeah.
Okay.
I didn't have possible examples till now. Maybe I'll have examples in the next part.
Okay, sir. Thank you.
So I'll just show a few small applications and before I summarize. So one is if you look at examples like a speech-to-speech, if you want to do speech-to-speech translation. So what things had happened in the past is the translation was understood more like appreciated as a language translation, and story was always about like, can you translate like a say English to Hindi? And it's always in text. Now people talk a lot more about speech-to-speech because I would like to talk to you in a more natural way, where I should be able to speak and I should be able to translate and listen in speech. So you can, as you can easily see, you can have things like speech, that ASR and TTS, the two important blocks come. This makes it speech-to-speech translation. You can think of one more level further. You can also think of now face-to-face, because if I am using a video call and I'm talking to you, I should be able to speak in my language and you should be able to hear in your language, and everything should be quite natural. So how do we move into that direction? So here's an example. So if you want to do such face-to-face translation, so you need all these sort of pieces that we talk till now in different ways to be used. I'll just show you a motivating video so you appreciate where the world could move as we move forward.
So, now given texts in different languages, we can get the corresponding talking face videos. If these texts are from a different language, we can use neural machine translation models to translate them into the desired target language. Furthermore, if the input is given as speech instead of text, we can even recognize this text using existing ASR systems. We are now ready to translate a talking face video in one language into a talking face video in another language. Here is a demo of how two people can, in the future, interact over a video call, even though they do not have a common language. We have a male speaker who knows only Hindi and a lady who knows only English. In their phones, both of them see a face-to-face translated video of the other person.
क्या आप जानते हैं कि मैं वास्तव में कौन सी भाषा बोल रहा हूँ?
Do you know which language I am actually speaking?
You are speaking in Hindi, but I can see you speaking in English. आप हिंदी में बोल रहे हैं, लेकिन मैं आपको अंग्रेजी में बोलते हुए देख सकता हूँ.
मैं भी आपको हिंदी में बात करते हुए देख रहा हूँ.
I also see you speaking in Hindi.
One day we will all be able to video call each other like this in different languages. एक दिन हम सभी एक दूसरे को विभिन्न भाषाओं में वीडियो कॉल कर सकेंगे.
मुझे लगता है कि यह एक शानदार अनुभव होगा.
I think it would be a wonderful experience.
So you see the systematic evolution of the space of translation from simple text to text to speech and face to face, and if possible beyond this as we move forward. I want to take this forward. So with one more example here.
I'd like to be a queen of people's hearts in people's hearts, but I don't see myself being queen of this country.
मैं लोगों के दिलों की रानी बनना चाहूंगी, लेकिन मैं खुद को इस देश की रानी के रूप में नहीं देखती.
I'll show you another example.
My name is Tony Stark, and I'm not afraid of you. I know you're a coward, so I've decided.
Mein Name ist Tony Stark und ich habe keine Angst vor dir. Ich weiß, dass du ein Feigling bist. Ich habe also entschieden.
Mi chiamo Tony Stark e non mi fai paura. So che sei un codardo, perciò ho deciso.
Meu nome é Tony Stark, eu não tenho medo de você. Sei que você é covarde. Então eu decidi.
Mi nombre es Tony Stark y no me das miedo. Sé que eres un cobarde. Así que decidí...
माफी चाहूंगा, पर मुझे बादशाह नहीं बनना। मुझे ये सब नहीं करना आता। किसी पर भी हुकूमत नहीं करनी।
You know it very well. I'm not successful, and I'm not in a position that I can come up to your father and talk to him.
So you see different examples here, and we know how, like, if you want to really appreciate, you need to see what the movie industry today put effort in creating such movies across languages. So here's another example.
Das Gebiet der Computervision bewegt sich aufgrund des Aufkommens des tiefen Lernens sehr schnell. Zum Beispiel verwenden selbstfahrende Autos sie jetzt, um eine Vielzahl von Dingen zu erledigen.
So you want to learn from...
I'll go around. Wait for my call.
So for a varieties of users, this sort of like a technologies are very useful. So I just want to... So we saw a set of capabilities of such, say translations, as well as the syncing or multimodal like knowledge transfer. Now, let us look at what more we can do. So we know that this capability to generate, so we are able to generate now, which means there is some redundancy, possibly across these modalities. And is it possible for us to reduce this, remove this redundancy so that there are utility from the system's point of view? What is system's point of view? Say compute or network or something like that. So here's an example where we have been struggling with the network connectivity. Many of us have poor network connectivity, and this has been a concern particularly during pandemic, particularly for educational content.
First operation that you have to do is the sampling operation. So for sampling, what we do is, instead of considering the signal values at every possible value of t, what we do is we consider the signal values at certain discrete values of t. So here in this figure it is shown that we assume the value of the signal xt at t equal to 0. We also consider the value of the signal xt at t equal to 2 delta ts, assume the value of signal xt at t equal to delta 2 ts, at t equal to delta 3 ts, and so on. So instead of considering the signal values at every possible instant.
So in a way this is reconstructed. So what is required for reconstructing is only a small set of frames and the speech, which potential implications of saving the bandwidth.
Shami Bhaiya, I think he was doing rehab and he was bowling at a very 120 wala pace, like for us, something utna pace pe. But I thought, okay, he's gonna bowl 120 and he promised कि वो मुझे body पे ball नहीं खिलाएंगे.
So you realize that such capability, if you are not dependent on every frame of it or every time, it's like you can fill the missing pieces, you can compromise, or you can say fill things and provide the sufficient user experience. So there are many more applications. I think I'll not go to the details at this stage. So there are a number of assistive applications, media, entertainment, system level implications in compression, communication type of things. There are a number of signal level implications for such technologies. So for example, if you are speaking, say assume you are taking a phone call in a noisy environment, can this sort of say correlations across modality help you to say denoise? So for example, if I'm using I'm speaking in the middle of the market, I would like the market noise to be removed, because I know that the system knows that by looking at my lips that what you need is only the speech that is coming from this primary speaker. So a number of such the directions exist beyond what we discussed today. So to summarize in the last piece, the lessons and path ahead. So we had seen the video content generation. Say a driving speech can generate videos in many useful, very interesting use cases in education, entertainment, sports, communication, and many other things. It can help in a translation. So you can also connect with other language modules, like a machine translation or ASR or TTS, etc., and generate a set of very useful, powerful cases for distribution, particularly in a country like ours, which is inherently multilingual. This sort of technologies will be very, very important as we move forward. So this entire thing requires a number of audio, visual, language technologies today to make this happen. They are the backbone, and they get used in different forms. So though you saw different type of application, but when you get closer, you realize they are all using this sort of 2-3 pieces, the relationship between the speech, the text, and face or lips. But there are other things, as I mentioned, about gesture, expression, sign language, and many other things that another set of things as we move forward, we will see on the emerging. So directions. So just to summarize, so this interoperability is very, very important, because if there are people with the disabilities in one modality or one modality of perceptions, this is a way of replacing and providing alternate assistance. And so this is good. This could open up systematic ways of providing assistive solutions. So this also gives you more natural human-computer interfaces. So very different. So the human-computer interface is super important, because we all use such computing or machines, and ease in use is important. Naturalness is very important. Naturalness is important for even if, say, for example, as I mentioned, a movie where some part is not synced well, you just struggle to perceive. You're distracted by that. So there's a lot of interesting things possible in the human-computer interface space. Now, so when you're generating such natural videos or images, etc., there is always a concern in terms of is there any ethical implication for such things or impersonation of that? So creating such natural things, whether it is starting from whether you are taking a camera to create naturalness, to every level of naturalness getting captured in the digital form, the transition from the physical world to the digital world, when the sensors and the generation capability become more and more, there is a worry about it. There is a natural to have that worry, and we need to address and understand such implications of that and worry about that. The capability to synthesize. So now another way to appreciate is we are all interested in analyzing or understanding. So we want to understand the face, we want to understand the expressions, we want to understand the speech, we want to understand the text. So, but the another way to ask this question is capability to synthesize has anything to do with capability to analyze? Or is the capability to synthesize reflecting our capability to analyze? So these two go in hand. If you are able to analyze, you are also able to synthesize. So if you are able to read and understand, you are able to reproduce it. So these two capabilities go in hand. So we have to understand that there is only, so when we started, if you remember the first two slides that we had, the capability to discriminate and capability to generate. These two are these two will go hand in hand as we move forward. We have to understand that they are not two different pieces. And finally, this modality help in better understanding of other modalities? For example, if you want to understand images, videos, can speech, NLP help us? Or the reverse. If I want to understand language, can say vision, images, videos help? So this issue of somehow for whatever reason we have split this entire area into multiple sub areas and have been working more like a independent watertight compartments. Now we see the compartments are becoming more and more porous, we see a lot of cross connection across these areas. Maybe we will see these areas coming still closer, or this is the best that we can come closer. I don't know at this stage. Thank you. So feel free to ask any comments, questions, etc. So I would like to especially thank the students who did most of the hard work behind. So the faculty collaborators, funding agencies, and of course the researchers who made the resources available on internet and catalyzed research. I also do an announcement. I'm looking for people to work on such problems in the future. Thank you. Back to organizers. If you have any questions, feel free to write in the chat. I'll try to answer to my best of my knowledge.
Thank you very much, Professor, for such a wonderful talk. So the way you have presented your work through the videos, is really appreciable. I hope the student would have understood all the lectures. So now, participants, if you have any questions, you may ask. You may raise your hands or directly you can message to the sir. Yeah, Devika.
Hi, sir. Yeah, yes, sir. So my question is like, in case of distinguished person, if somebody start like do something not to spoil his figure, a very distinguished person, like this, like a generated video from a person, but without his consent, can machine do something against it?
Yes. So that's a very interesting question. So we have to understand, as I mentioned, that the capability to analyze and capability to synthesize go in hand. So we have to put where the technology is heading on the table. So we have to understand, and there's a very, very interesting open problem that we need to understand. So where this how machines can detect, how machines can detect the type of issues that you mentioned.